right, take a seat there, seat in the front. Okay, good afternoon. Let's get started. All right. Today we're going to wrap up chapter 2. All right. So last time we have been talking about stress in a bar that under axial load. So we were looking at if you look inside the bar, right? Depending on which direction you are looking. If you make a perpendicular cut, the cross sections, you're going to have only the normal stress, right? That will be sigma equals to. Okay, what's the stress if you just do the normal part? It was working fine. Okay, now let's go to short side. Still not taking the pen. Okay, let's do this way. We can make it a little bit bigger. Okay, so if you cut perpendicular, right? So we know the stress will be sigma equals to P over A. That's what we already know before. Now, but if you cut a direction that's not perpendicular, right? We call it inclined surface. Then on that surface, you're going to have both normal stress and the shear stress. And we derived the equation. We came to the conclusion, and this is the expression. So for the stress, you're going to have normal and shear. Right? And then we did the analysis about this equation. So you find out what's the maximum, what's the minimum, because this is changing with the angle theta. When you cut a different direction, the stress is going to be different. And we find out, okay, at 45 degree, if you look at the stress, the shear is going to be maximum. Right? So if something going to fail, and because the shear stress is too high, then the direction will be 45. So the crack will generate a 45 degree. Right? However, if you have a material that fails by normal stress, because the normal stress is just too high, right? And that the material will fail in the perpendicular direction, right? They will break that direction. So by looking at how the material fail, you can actually judge what kind of stress was it under, and what's the reason causes the failure. So that basically you can do the analysis. All right? So today we're going to look at the one concept that's called straignergy. All right? So we talked about the energy before, and I think in physics, right? We always say if you deform something, or if you, let's say you put something to a higher location, you're going to accumulate potential energy, right? Because when you release it, this will fall down. The gravity will pull it down. That you have a potential energy. Right? And when you moving something a distance, then you're going to do a work, right? So we calculate the work, right? Anyone remember the work? How do you calculate the work? It will be the force times the distance. Right? But that means, okay, the condition is you have a force, constant force, applying on surface. So you have something here on this flat surface, and you're moving an object. Let's say this is the weight W, and you're applying force F, and you move it to somewhere here, right? So that travel a distance S. So at a constant force, you move an object a distance S, then the work done will be the force times the distance. Okay, that's the ideal situation, constant force at distance. But in many situations, you're going to have variable force. How do we calculate the work done by a force that's changing with location and with time? Integral. So you look at this one segment, treat it as a constant, calculate the work here, calculate work here, then you integrate them, right? So put it mathematically, what you have will be the equation like this. Okay. So I think I'll change to the slideshow instead of writing. I'll change it back when I need to write things. Okay. All right. So you're going to have to do the integral calculation. So you calculate the force at each small travel distance. Calculate the work there, and then put them together. That's how you calculate the work, right? Okay, so that we learned actually previously from physics. Right. Now, when you apply a force to a bar, try to deform it, right? So you apply a force. Now, you are moving a distance, right? We said that the bar will elongate the distance delta. So by that concept, you pulling something with a force. You move a distance. Then what you are doing? You are doing a work, right? So you do a work, and that actually can calculate how much you did there. Okay, so remember we talked about linear elastic. Okay, so when you deform something, you're applying force, and you're going to generate the delta. So the force and the elongation, they are proportional. We talk about linear like a spring, right? Although this spring, not like a coil, can be a bar. So basically, a bar is like a spring, because when you pull it, it will deform. The more you pull it, the higher force, the larger deformation, right? And this relation always linear, right? We actually had this equation. Actually, it's not here. So we had this equation. Let me just write on the board. So delta will be PL over EA, right? That's the relation. So this is a linear equation. So in a sense, when we talk about a bar is basically a spring. You are deforming. It's just a very hard spring. Because when you apply a huge force, it's deformed only a little tiny distance. It's not like what we see in common daily life, you see a spring. So when you put a little bit of force, you can deform huge. You can visually see a large deformation. But anyway, the concept is the same. So you pull it, the deformation proportional to the load. Or another way, the load proportional to the displacement. So it's a spring. Okay, so the force is, in a sense, the more you pull it, the more force you're going to have. So therefore, when you move it something from point A to point B, you push a bar. And you actually have to keep increase your force, and then you can be able to move a larger distance, right? So the force is always proportional to the distance. So I can put it this way. So the force is proportional, so the Fx equals to Kx. So it's proportional. Therefore, in this case, when you try to calculate the work done, right, you can put the force into this integral equation. And you put it there, so Kx, you put it inside the integral, and you do the calculation, right? Integral x, integrate once, that's going to be a square. So you end up this term, right? Okay. So that means when you apply a force to generate an elongation delta, the work you done is actually proportional to the delta squared, right? So that means it's not linear. Right? So this one, actually, we can change back to force P, because the P equals K delta. And so if you put it back there, then you end up with this equation, the last one. So the work, actually, is half the P times delta. It's like a linear spring. When you pull this distance, the work you done is actually half the force times the distance, right? So this one actually can easily illustrate by this figure here, right? The force is changing. So therefore, when you do the integral, you don't have P delta. You actually have half the P delta, because the area that's covered there is half of this, right? It's a triangle. So this triangle area is half the P delta. Right? If you have a constant force, right, then you have this P times delta, because that's all the square area. Now you have only half of the area. So that's why it's half. Okay. So remember, when we talk about linear elastic deformations, the work done is always, there is a half there. So it's half the load times the distance. Right. So that's the work when you pull a bar. Now, where this work you done, where does this energy go? You're pulling, right? You're doing a work. Where does this go? into this bar. It's stored there as the energy. Why is the energy? Because when you let it go, what happens? It will pull back, right? The pull back is moved because there is energy stored in that piece of material, that bar. And so therefore, we say, okay, when you pull in a bar, you are deforming a bar, and that generates energy inside this bar. And this energy comes from deformation. So therefore, we call it strain energy. Deformation is strain, right? Strain is deformation. So we call this kind of energy is stored in a deformable object. We call it strain energy. And the way for a bar, you can calculate very simple this equation for linear elasticity. Okay, so that's a simple concept, actually, continue from physics. So we know, okay, when you deform it, you do a work, and you store energy there. And that's exactly the same amount. Right? Because we don't consider dissipation. We think everything is preserved there, right? No loss of energy. So therefore, U will be equal to W. Okay. So that's just a simple concept. But actually, when we're doing complicated systems, we use the energy concept a lot. That's why we need to build this concept of straining. Right? Okay, so for a bar, we know the deformation will be given by this equation, delta equals PL over EA. And the energy is P delta then over 2. Right? So with these two equations, you can actually derive lots of different expressions. You can cancel out delta, find out the U related to P. Or you can cancel out P, find the relation between U and the delta. They're all square relation, right? So parabolic relation. But the basic equations are these two. So that's how you calculate the energy, how you determine the deformation. Right. Okay, so this is the variation. See here, what I'm trying to say is this, the equation I just showed here, you don't need, no need at all to memorize it. It's just when you see it, don't feel strange why there is a square there. Right? Because those bottom two expressions came from the first two equations. You combine the first two equations, that will give you this one. Okay. So when you try to remember things, remember the basic equations. Now these derived equations, you just do a quick derivation look at it. All right, so as I mentioned, so we need the energy. Basically, we can use it to solve lots of complicated problems. All right, and so here I want to go over one very simple example, just to show we can use the energy to solve a problem to find out the deformation. Right? For example, from this equation, right, here U equals P delta over 2. And you can easily find out, okay, delta actually equals 2U over P. Right? In other words, if I can find the U, the energy of the system, then I divide P. That will give me the deformation. Right? So here, let's go over one simple example and see how we can actually use it. Right? I don't think I can write it here. Yeah, still somehow I couldn't. Okay, so I'll go back to this one here. Okay, so let's use this one. All right, let's use this slide. We can actually try to write the equation, how we can solve this problem. All right. Okay, so for this problem, we need to find out when you pull with a load P, how much distance movement you're going to get. We want to use the energy method. Okay. All right. So when you use the energy method, basically you need to find out the energy that's stored in the bar, right? Because we know the energy U, that's what we just wrote there. U equals W. So if I find the U, find out W, then I can use this equation and find whatever is unknown there. Right? Okay, so we need to find out the U and the W. Actually, for W, we can easily find it. What's the W? If I apply a force P to the system, right, I stretch it, it will deform by this point going to move by distance, let's say delta. Right? How much work is done? So it will be P times delta over 2. Yes, remember this half. Right? So I know the this equation, right? Okay, so now I know I'm applying force P. So if I can find out W, then I know delta. Okay, how can I find W? I have to find out U. Okay, how can I find out U? U is we call it strange function, right? Strange. So we need to find out these two bars, how much energy you're going to store in these two bars, right? Okay, how do you determine the energy in a bar? Remember this basic equation. U equals to the force in the bar, right? Times the elongation of the bar, and then over 2. Is that correct? Right? Remember this equation? We had U equals to W equals to half P delta. That's the equation we just said. That's the basic equation. Now, in this case, right, you need for the bar, there are two bars. They're same. Let's say they're the same. So I just need to find one of them. Then it will be double. Okay, so for this bar, how can I find the energy? It's the force applied to the bar and the elongation of the bar, right? Okay, so the force in the bar is N. That's the internal force. Then the delta will be the elongation of that bar. Right? So I need the force in that bar. Okay, how can I find the force in that bar? I know the load. Okay, I know the structure. I apply load. How can I find the internal force in a bar? Equilibrium, right? You have to do a free body diagram. Then write the equation of equilibrium. Okay, let me just draw it here since we don't see that picture. So you have this here, right? So you're applying force P here. Now what you need is the force N here in this bar. And you know the load here. So how the N and the P are related? You need a free body diagram. And then you write the equation of equilibrium. Okay, let's say I pick this point as my free body. So I'm going to have this free body diagram. P applying here. Then you have N here. Then there is another N here. Right? And then this point is in equilibrium. Okay, what's the equation of equilibrium for this point? You have sigma fx equals 0. Right? That's why the 2n, I say it's equal. I kind of assume it's symmetric, so I put it 0 there. Now, sigma fx equals 0, automatically satisfied. Now, so the only equation that I haven't used will be sigma fy equals 0. Okay, translate that. You have n times, depending on which angle, right? Let's call this angle alpha. So you have cosine alpha, and then another n, cosine alpha. So you have two of them, right? One on the left side, one on the right. And then minus p equals 0. All right? Okay, now can I find out the n from here? Yes, so I got n. So n will be equal to p over 2 cosine alpha. All right? Okay, now I find out the n. Now, do I need to find out the delta here? Remember, I tried to determine u, right? Because once I know u, I know w, then I find out this. So you can use this equation, right? Delta in this bar, 1. So let's call 1, right? So this will be 1, because I try to distinguish between these two delta. So this will be n1 delta 1. Right? And that will be n1 L E A. Yeah. So I can find delta 1, then put it here. Right? Or is there another way? I don't need to calculate delta. Delta 1, I mean. Can I just use this equation? See, this one here, because u is n times delta over 2. But delta has this equation. So can I write this way? So I say u will equals to half of this n times this. So n's 1 square, L over EA. I just directly use this equation. Right? Then you can put n1 there, find out the u. Now, next you will just connect this equation and this equation. Connect these two. You'll find out delta. I'm sorry?
How did you get
Okay, this one. Okay, how can we get this equation? That's the one I think you show here. See, this equation. The basic equation, top two, right? You can combine derived equation. So it's a derived equation. Right? U is the strain energy. We call strain energy because that's the deformation generated energy stored in the bar. So we call strain energy. Right? Okay. So for example, for the exam, I'll provide you a formula sheet. I'll give you the two top equations, the basic one, but I won't give you the bottom one. And so you can use the top one, you can easily just get the bottom one. Right? Because otherwise, there's just too many equations. I just want to stay with the basic equations. All right. Okay, so see, that's very quick. Now we've got the solution. So you can see the advantage of using energy method. Because you combine these two, you immediately get the delta. Okay. All right, yes?
For the length, are we going to use the height that's given in the diagram, or are we going to use that, the length of the actual?
Okay, now this is my question. When you use this equation, oh, okay, actually I can just, when you use this equation, what's the length you use here?
The length of the bar itself.
Yeah, it's the length of the bar, right? So therefore, when you put it here, it should be the length of the bar. Right? Because when you use delta equals NL over EA, the definition of N is the local uniform local load force. And the L will be the length of that bar. So you have to use the length of the bar. It's not the height.
Okay. Oh,
right.
So even though we only have the X component or the Y component of that.
Yeah, so let me go back to this picture. Okay. So what I mean is we need to use the length of AB from point A to point B. That's the length of the bar, because that's the bar that's deforming. So you put the length of the bar in there.
Okay.
All right. Someone has a question? Yeah. Multiply what by 2? The work? Let me see here. Okay, you talk about maybe I typo here. Let's see what I put here. See, there's a 2 already here. So it's 1 over 2, right? Always there is when you calculate the energy, there is always 1 over 2. Right? So now when you combine these two equations, see here is a 1 over 2. Here is 1 over 2. So this will cancel out. Right? You're going to combine, let me just point here. Okay, so you combine this equation equal to this part. That gives you solution. Then this side you have a half, this side you have a half, so you just cancel out. All right. Okay, any other questions? Okay, next slide. We'll bring up another concept called strain energy density. Okay, what density mean? Density, that's a common word we use, right? Mass have a density, heat density, energy density, right? Your money density, that's how much you get per month, right? So density basically say how intense, how much energy you put in your bar, right? So by that we mean the total energy divide the volume, so per unit volume, right? So therefore we define the energy density, or actually strain energy density, as small u, use small u to represent it. So that's the capital U over the volume V. Now, if you plug, what's the U we already have, and then what's the volume V? Because V is the area, cross-sectional area times length, right, of the bar. So when you plug that in, you actually get a very simplified equation. That is U equals half sigma epsilon. So it's a very nice form. You can say stress times strain divided by 2. That gives you strain density. Right? So it works out beautifully, just very nice format. Okay. So the density, remember, density is the energy per unit volume. Right? In this case, because we have everything there in the bar is uniform. That's why you can divide the total volume. Right? And later on, we're going to have situation. The energy is not uniform distributed. Then you have to calculate locally, each location, they have different energy density. But in this case, because everything, remember we said the stress is same everywhere, right? and therefore the energy is the same everywhere. I mean, the density is the same everywhere. Right. Okay, so we come up two concepts. One is strain energy function. Okay, a strain energy. One is the strain energy density. So these two are related. Okay, any questions about strain energy and density? Okay, so next I want to go over a few slides just to show you, it's for fun, just you look at it, to show you when you have a bar, right? You pull on it, we know if you have a uniform bar, you're going to have a stress, sigma equals P over A. And that stress is the same everywhere. When you look at any point in the bar, it will be the same, right? But also, remember, we talk about non-uniform bars. When you have a non-uniform bar, right, how the stress is distributed. So I want to show that here. Okay, so this is a situation when you have a uniform bar, right? And you're applying load. What actually applying here, this is actually done by from a student from our class, from this class. So he just did this extra credit project. So basically use a finite element, numerical tool to do analysis. So you put a bar in this computational software, and then you apply a force from the right. That's where you see the right point there. So you have applying force there. When you're applying force there, this is the stress map. So color representing stress level. You can see over the majority area, it's all blue. That means the stress is pretty uniform, right? That confirm the stress is uniform, the assumption we made. But however, if you look at the tips, the edge, right, there are always high stress or can be low stress as well. So basically, when you apply the load, can be locally, you may have some high stress there. But if you have a long bar, and that area will be tiny, so we can ignore it. So we always assume, oh, this is uniform everywhere, because we just ignore that small portion of it. Okay, in this class, we never talk about these edges, how high the stress will be. If you want to find out that, you will need more advanced courses to learn mechanics, and then there will be equation you can determine that. Okay, but that's beyond our scope. All right. Okay, so here is another example. If you have non-uniform bars, right? This one, you have one part, the bigger cross-section, than the other part. And this is the load, the pink arrow showing where the load is applying. Okay, when you apply that, and the bottom one shows how the stress is distributed. You can see the transition area, you have the peak there. So there is a transition again. So there are this local high stress we call stress concentration. Right? But that stress concentration is very local, and we can ignore it once it's away from that local area. That's called Sullivan principle. You can read the textbook, it describes that in more text way. Okay, so that's the kind of stress distribution. Here's another example, and they show if there is a hole, you pull this bar, there is a hole in the middle, and that's what it looks like. So you can see again, in the majority area, stress pretty uniform, right? But you can see that part with the hole, it's a little bit yellow than the other part. That means the stress is a little bit higher than the other part. And in the transition locations, you see a few red spots. That means peak, high stress concentration. Okay, so this kind of a situation, how the stress is actually distributing in a bar. All right. So this one we already showed shear. Okay. So that's basically what we want to cover for chapter 2. Okay. So next 2 slides I put here just summarize what we already learned from chapter 1 and chapter 2. So that's basically will be in our exam 1 that come up next Friday. Right? I mean, a week from this Friday. Okay. So it's like 10 days away. Right. Okay. So here is the summary of, I think this is mostly from chapter 1. So the basic equations. The definition of normal stress, shear stress, and also the Hooke's law. Right? So remember Hooke's law, you have 2 parts. One is for normal stress, one for the shear stress. Either stress, you're going to have this Hooke's law. It's a simple linear relation. That's the easiest case. All right. Then we have the definition of Poisson's ratio, and also safety factor n. Right? So when you have safety factor n, then the allowable stress will be the yield stress divided by n. It's the same for shear stress or for normal stress. Right? And then the total load you can apply will be the allowable stress times the area you have there. Okay. So this one, I believe it's already online. If not active, I will activate after the class. So you will see this slide from our Blackboard. Right? Okay, so here's another slide, summarize chapter 2. Okay, so chapter 2, basically, we cover about a bar and the axial load. Right? So the load is the actual force you apply there. Remember, it's a force, not a movement. It's just a force. Okay, movement, we'll talk about it in chapter 3. So now we have just a force actually applied. And you're going to generate a deformation. We call it elongation because you're going to elongate. But actually, elongation, I mean, also can be a shrinkage when you have a negative elongation. Right? So basically, it's an elongation or shrinkage. It's a linear. All right. And then in this bar, you're going to have uniform stress, sigma equals PA. And the energy you can calculate by half of the PA delta. And the density, you just divide away, that's the stress. We just cover it. And then if you cut on inclined surface, you're going to have both normal stress and the shear stress. Okay. So here's a concept we need to have in our mind. When you have a bar, you can have both normal stress and shear stress in this bar, depending on which way you cut it, which way you look at, right? I mean, which direction you look at. All right. So don't answer me, all the shear stress will be 0 because there will be only, normal pulling there. Okay, I can have shear stress 30 degree if I cut it, or 20 degree if I cut it, then you're going to have those. All right. Okay, then if you have a non-uniform bar, we have to divide it into several segments. And then you calculate the elongation of each segment and add them together. That gives you the total elongation of the segment. Right. So that's what the concept of non-uniform bar. Actually, you should put the word there, not just a series of bars. We call non-uniform bar. Okay. What do you mean by non-uniform? Can be different cross-sectional area, different material, right? Or different load, different internal force, or combination of all three, right? So that's all can be non-uniform. So it can be geometry, area different, material different, or load different. That's all not uniform. And the most challenging problem is when you have the load is not uniform, because people get the internal force wrong. And that's the common mistake there. Okay. So related to that, actually, I'm going to give you another quiz. Ask you to look at the local forces, internal forces. Just calculate the force, internal force. Right? So the calculation is easy, but the concept, I think, is important. So I'll give you one more opportunity to practice, get the internal force correct for non-uniform bar. All right? Okay. So the other assignment will come up. I think I will make it due Friday or Monday. I think we can make it. Okay. All right. I can look at the other deadlines, and then most likely I'll put it next Monday. All right. Okay. But it can be a Friday, so check it. All right. Okay. Then the last one. That's the most challenging part. That's the indeterminate problem. And that, we say you always use the fed.com approach. Right? So once you identify this problem is indeterminate, you go ahead use the fed.com. Okay. What if you don't know? Let me ask this question actually first. What if I say it's a determinant problem? What do? How do you solve it? You use just the fed part, right? Free body diagram, equation of equilibrium, then deformation. So you don't need the compatibility part, right? Okay, so that's the determinant part. Now, indeterminate, we use the whole thing. Now, what if I don't know? I cannot judge in advance. So you just go ahead, start with the F part, then do the E part, then do the D part. But then you should know it's determinate or indeterminate. Right? And then you say, oh, I need the compatibility, or I don't need the compatibility. Right? So, therefore, if you cannot judge it's determinate or indeterminate in advance, that's okay. You just go ahead, still do it. And then in the middle, When you write out the equation, then you find, oh, I cannot determine all the unknowns, so it's indeterminate. Right? So it doesn't actually affect you solving the problem if you cannot judge in advance. But we do have things you can actually practice, give kind of common situations, you can judge it's determinate or indeterminate. All right. Okay, there's a question? Okay. All right, so this part, that's the most challenging part. So my suggestion is do a few more homework problems from the textbook, not just the one assigned. Try a few other ones. This one looks strange. Okay, let me try it, see if you can solve it. All right. And so this way, you know, you want to make sure all different kinds of indeterminate problems, you can solve it. Right? Of course, it can be a misfit or thermal stress associated with it. All right. Okay, any questions about this sum? This will be, this 2 slides, summary slide. It will be online. You can see it there. Yeah. Yeah, so I will give you a formula sheet. So you can see formula sheet, right? And this, we're doing this way. So you don't bring anything. And, of course, calculator you can bring, right? Your head, your brain you have to bring. Then we'll provide the formula sheet, right? The reason is I think lots of times, somehow, when I ask everyone prepare their own formula sheet, people miss the equations, put the wrong equation there. Somehow they just copy the wrong equation there. Then, you know, everything will. Okay. But the one thing you need to do is get familiar with this sheet there. Say, what's the P there mean? What's the A there mean? What's the L there mean? I won't explain to you. Because that's you're supposed to know that already. I won't change the letter suddenly to a different letter. But you're familiar with this sheet there. What's the sigma there mean? What's the epsilon there mean? You need to know their meaning. What's the equation mean? Okay, that's the part you need to prepare. You need to know it. All right. Okay, other questions?